In dealing with chemical reactions and looking at thermodynamic calculations with chemical reactions, we need a way to be able to account for the fact that when the bonds are either breaking or forming, there can be a change in the energy of the system. And so consequently, what we're going to do now, we're going to introduce a new property, and that is called the enthalpy of formation. And also, if it's an oxidation reaction, it turns out to be enthalpy of combustion. But we'll take a look at that in this segment, and I'll show you how we do or handle this enthalpy of formation. So if you recall, we've been looking at a number of different properties that are very useful for thermodynamic calculations. So what I'm going to do now, I'm going to give a paragraph for each of the different main properties that we've been using, such as internal energy and enthalpy. And then what I'll do is I'll proceed to contrast these properties with what we need for this new enthalpy of formation. So we'll begin with internal energy. So for internal energy, what we were dealing with was basically accounting for the kinetic energy of the molecular motion within the substance that we would be looking at. And the higher the temperature of the, usually it was a gas, but it could also be for a liquid, you'd have a molecular motion there. But the higher the temperature, the higher the internal energy, and consequently this was a form of what we called sensible energy. So that was the first treatment of internal energy. We also had internal energy associated with a phase change, when a substance would go from either a liquid to a vapor, or from a vapor back to a liquid, or it could also account for when it's going from a solid to a liquid. So in this course, when we look at internal energy for a phase change, we would use the subscript Fg to denote that. And this is usually in this course what we're looking at, it would be our working fluid either going through boiling, so going from liquid to vapor, or condensing from vapor back to liquid. And this is what we refer to as being latent energy. Sensible energy is without a phase change, it's just a temperature change. When you get into the phase change process, it becomes latent energy. And so that was another way that we looked at the property data. The next thing that I'll do is I'll take a look at enthalpy. So when we looked at enthalpy, we saw enthalpy applied to a fixed mass system. And essentially what enthalpy is doing there is it accounts for both internal energy as well as boundary work. And that was for a fixed mass, constant pressure process. So that was one way that we were applying the enthalpy for a fixed mass system. It also applied or covered the flow work term for a steady flow process. That would be for an open control volume where we have mass crossing the control boundary. So enthalpy was another property that we've dealt with. But what we're now faced with, so we've looked at internal energy, we've looked at enthalpy. We now need a property that enables us to take into account the fact that when we have bonds breaking or forming, there could be energy exchange. So this is something that we have not looked at yet in the course. And we need to be able to account for this when we're dealing with chemical reactions, such as what we would have within a system undergoing oxidation or combustion reactions. So what we need is we need a form of enthalpy that can help us, internal energy or enthalpy, that accounts for the change of energy when bonds are broken and formed. And in order to do that, we introduce this new property or value called the enthalpy of formation. And the symbol that we use for enthalpy of formation will be H, just like normal enthalpy. We're going to put an overbar on it, and that is because we're going to give it in units per kilomole basis. We are going to put a 0 in the subscript position because that denotes that it is referenced to a standard reference state, which is 25 degrees C in 1 atmosphere. And finally, we will give it a subscript F to denote formation. So the different things that we have, the overbar, that's because it's on a per kilomole basis, which we will find to be quite convenient when we're dealing with stoichiometry and chemical reactions and the balance, the number of kilomoles either on the reactant or the product side. The 0 references to a standard reference state. So that means that this property has been determined at a standard reference state. And that standard state by convention is 25 degrees C and 1 atmosphere. And finally, the subscript F refers to enthalpy of formation. So that is the enthalpy of formation, and we'll be using that as we work through problems involving chemical reactions and combustion. So when we're dealing with these problems, we're going to be dealing with a lot of different components or species. For example, we could have oxygen, nitrogen, carbon dioxide, carbon. But no matter what we're doing, we always need to reference the enthalpy for all the components that we have in our system to a standard reference state. So as an example, let's take a look at the enthalpy of oxygen. And let's say we want to look at it at 790 Kelvin. So what we would need to do, given that we're not at the 25 degrees C reference state, we would need to look in the back of our books and look for a table dealing with ideal gas properties of oxygen, O2. And what you'll find, these tables will be tabulated in a per kilomole basis, and you'll find the value for enthalpy at 790 Kelvin, and then what you would do is you would subtract off the value of enthalpy at the 0 reference state, which in this particular case would be the per kilomole basis at 298 Kelvin. So you would take off the value at 298 Kelvin, and that would enable you to determine the enthalpy at 790 K. You could then tack that on to the value, the heat of formation for enthalpy of oxygen, if that's what you needed in a calculation. We'll see that in an example in a minute, but what you would get if you look in the tables in your book, so those are the values for oxygen. We would find 15,504 kilojoules per kilomole. So that would be the enthalpy with respect to the reference state of 25 degrees C. And you would then use that in combination with your heat of formation. So then what you would do is you would go and you'd find your enthalpy of formation tables, which again will be in the back of your textbook. And what they will list is they will provide enthalpy of formation at the base state, so at 25 degrees C, 1 atmosphere. and they will be listed for different substances that you might be dealing with. And you'll also notice that there will be values for carbon, hydrogen, nitrogen, or oxygen, which it turns out that this is what all of the substances that we have enthalpy of formation are with respect to. But interesting, if you look at the enthalpy of formation for these four substances, carbon, hydrogen, nitrogen, and oxygen, if you look in your enthalpy of formation table, you'll find that the heat of formation value for those four substances is 0. And that's because everything is being formed from those, and consequently they are given the reference state value of 0. And then other substances, for example, if I look in the table here, we have things like carbon monoxide. So we could have carbon monoxide in the gaseous state, and you can get the heat of formation for that, and that turns out to be minus 110, 530 kilojoules per kilomole. Now that would give me the heat of formation value at 25 degrees C and 1 atmosphere. If I had this in an equation that we'll see in a later segment where we're dealing with the first law, I would need to correct that value for the enthalpy at whatever particular temperature we would be dealing with for that substance. And so that's a correction that we'll see as I work an example in a later segment. But anyways, that is the enthalpy of formation. What it does, it takes into account chemical bond energy and the change of energy associated with either the breaking or the formation of those bonds. And so we'll be dealing with this as we continue to do calculations involving combustion.